This video shows you how Harvey and co-authors in 1993 transformed the nonlinear stochastic volatility model to a linear model. Now remember, the data generating process of the stochastic volatility model is characterized by the following three equations. So you have xt be the shock to the return, eta t is the shock to deviations of volatility from its expectation, and then we have a correlation between return and volatility shocks. Again, just to summarize, remember here that the model for RT is nonlinear because ht and xt enter multiplicatively into the return data generating process. So estimating a nonlinear model is complicated. Now Harvey and co-authors in 1993 suggest a way to linearize the model. So let's understand what they do. They argue, or propose, better to say, to take the natural logarithm of the squared zero mean return to get the following expression. The log of RT square would be the log of sigma upper bar to the power of 2 plus ht plus a random variable which they call epsilon t. Now epsilon t is just equivalent to the log of ct square. And one can show we don't do that. Take that as a result that epsilon t follows a log chi-square distribution with 1 degree of freedom with a mean of minus 1.27 and a variance of pi square half. Now the covariation between epsilon and eta is 0, and ht itself follows the AR1 process as above with an autocorrelation coefficient phi and a Gaussian shock eta. Now let me add a couple of points here. Now first, as xt is a standard normal, one could show that epsilon t follows that log chi-square distribution with 1 degree of freedom and a mean of minus 1.27 and the variance of pi square half. Now second, also note that information regarding the correlation coefficient between return shocks and vol shocks get lost if you apply that linearization. Now Harvey and Shepard in 1996 propose a way to solve that issue. Yet in that video here, I'm ignoring that. And third, and finally, Harvey and co-authors in 1993 propose to swap that log chi-square distribution with a Gaussian distribution that shares the same first and second moment. So maximizing such a distribution has the formal name of quasi-maximum likelihood. That says that we don't optimize the correct likelihood, but a conditional Gaussian likelihood with at least the correct first and second moments. And in fact, many empirical papers work with that quasi-maximum likelihood approach. The main reason is that the Gaussian bell curve shape has a convenient parametric expression that researchers enjoy working with. Now let's use that example to introduce you to some language that we're going to use in follow-up videos. Now here's what I mean. We are calling the observation RT to be coming out of a measurement equation. Now the measurement equation in that example reads the log of RT square, that's what we observe, what we measure, and that equals the log of sigma upper bar square plus ht plus epsilon t, where epsilon t has that Gaussian distribution. Now, in our language here, we are going to treat epsilon, the Gaussian variable, as the Gaussian measurement error. So notice, it's not a typo here that I use a Gaussian shock instead of the log chi-squared shock. And that is exactly why I mentioned before that approach will be a quasi-maximum likelihood approach and not a maximum likelihood approach. Now, second, in contrast to the observed time series R, the data generating process for the unobserved state variable ht is called state equation. So for that example here, the state equation reads ht equals phi times ht minus 1 plus eta t, and eta t follows the Gaussian shock, mean 0 and variance sigma square eta. So that application basically is the first application you see in my sequence of videos that falls into the class of a state space model, meaning you have an unobserved state and you have an observed measurement that depends on the state. So there is now one question which remains: how to maximize that conditionally Gaussian likelihood function, given that the time series for the realized HTs is a necessary input to evaluate the likelihood, but at the same time they are unobserved? Well, that indeed is an excellent question. And maybe surprisingly to you, a very similar question came up over 50 years ago when the NASA prepared for the first moon landing. The solution was developed around exactly that time and is called linear Kalman filter. So in short, it means that we are substituting the unobserved value of ht with its expectation, with its most likely realization. Now, as the expectation is of course not the same than the realized value, we will also increase the uncertainty around the likelihood to account for that. And you might have guessed, there will be a sequence of videos that I post that talk you through the estimation procedure of the linear Kalman filter.